We will now apply Stokes' theorem. We will consider the case of a circumference on the xy plane, and we are considering this circumference with the radius r, whose equation is x squared plus y squared equals r squared. As I said, we also have a vector field whose components are fx equal to minus y, whereas fy is equal to x. So minus y here, x, and then the third component is 0, or if you want, I will just consider these two components right here. We have to compute the line integral over this closed line, which is gamma, the circumference, I will call it gamma, of f dot dl. Stokes' theorem tells us that this is equal to the integral over a surface which has as a boundary this circumference, but I can take this area right here. I will first take this area right here, which is easier because we are on a plane. So we have to take the curl of f and then dot and ds. ds is just in this case dx dy because we are on the xy plane. Let's take the curl of f. We have a determinant to carry out. In the case of a two-dimensional plane, we just have to insert the first two components of our curl, d over dx and d over dy. Then in here we have minus y because it's fx, and then we have fy, which is x. And this is equal to, if we take the determinant, dx over dx, which is 1, minus, so it's plus dy or dy, so we get 2. And remember that this curl is pointing outwards of this plane, so its direction is k. So remember, this is a vector, so we get also a k here and here. So this integral becomes equal to integral of 2. We have k dot n, but n is also pointing outwards because we are traveling anti-clockwise in this circumference. So if you use our right-hand rule, as we move, our thumb gives us the direction along which the normal to the surface is pointing. So the dot product is just 1. So we get integral over 2 ds. Integral of ds, in this case, what is ds? The area of the circle, so pi r squared. So we get 2 pi r squared. Very easy. As you can see, it's much simpler than the way we computed it when we were doing line integrals. But let's do another example from here. Let's try to compute the same integral, but this is the circumference as seen on the xy plane, but in this case we will also consider the z-axis, so it's x, y, and z. And let's consider a hemisphere. So instead of computing the surface integral on the circle, let's compute it on the hemisphere, and this is part of a sphere, so this formula holds. X squared plus y squared plus z squared is equal to the radius squared of the sphere, but it's always equal to r. It's r squared. And what we need to do is to compute the surface integral in this case over this surface. So this is the same formula right here, but we need to find n, the normal to the sphere. What is the normal to the sphere? Well, the normal to the sphere is pointing along the radius direction. It's a radial direction, right? What is the radial direction? The radial direction is given by, if we use spherical coordinates, if you remember, x was equal to r. In this case, r is just the radius of the sphere because we are moving on a sphere. So r, and then we have, remember, this angle is phi, so we have r sine phi, because this is the projection of this vector on the xy plane. And then we need to consider cosine theta, whereas y is just r sine phi sine theta, whereas z is equal to r cosine phi. So the normal is just equal to, we just divide by r, because remember this must be unit normal, so we just take sine phi cosine theta, and then we have sine phi sine theta, and then we have cosine phi. If you take a look at this, if you square the components and sum them, you get 1. So this is the unit normally. We have already done that some lectures ago. You have to take the curl, but the curl is always the same. It's just 2k. That doesn't change because the field component along z is 0. So we just get that. All in all, we get an integral of 2k k dot n, but k dot n is just cosine phi, so we get 2 cosine phi times ds. In this case, ds is the surface of the hemisphere, so we have to integrate over this one, and this is not equal to dx dy. In this case it was equal to dx dy, but in this case it is not. We need to express ds in terms of polar coordinates, but we had already done that. We know the formulas, so I will not do the steps again here. This is just equal to r squared times sine phi d phi d theta. We need to integrate over the hemisphere, not the sphere. Okay, so we have 2r squared, and then we have an integral, okay, double integral, because we are integrating over d phi and d theta. So it's cosine phi sine phi times d phi d theta. Theta ranges from 0 to 2 pi because we're integrating over the entire range of thetas. So this is 0 to 2 pi, whereas the range for phi is not anymore from 0 to 2 pi because we have to integrate from here to here, so it's from 0 to pi over 2. Okay? The integral over theta is very easy, it gives us 2 pi, so we get equal to, we get 2r squared times 2 pi, and then if we take the integral of cosine phi sine phi, this gives us sine squared phi over 2. This is just the integral from 0 to pi over 2. This gives us 1/2, as you can see. The derivative of sine squared phi over 2 just gives us cosine phi sine phi. You can do that, it's very easy. This is 1/2, so we get 2 divided by 2, and this gives us 2 pi r squared. And as you can see, we get the same result.